2, 3, we're recording. All right, we're live. Everyone say hi. Oh, there you go. That's BC Calculus. All right, 2021. Star Trek Day. So, as we were saying, Mason, I didn't find a comb during lunch either, man. Yeah, my wife asks me every day. She looks at me and she goes like, so what's the plan? That's what she says. She just walks up to me. So what's the plan? And I'm like, I have no idea, honey. You're in charge, right? And she's talking about my hair, and I'm just like, I don't know. I really don't know. I mean, pretty soon I can get it back. So, out of the way, in a ponytail. But then she's like, well, why not just cut it off? If you're just going to put it in ponytail, you're going to pull it back. Why even have it? I'm like, that's a good point, but I don't have an answer to that. She's like, if you're going to go by Bob, don't name yourself Robert, right? Why just name yourself Bob? She's like that. She's like, no nonsense. She does have an uncle whose name is Bob. And I guess it runs in the family because on his birth certificate, it says Bob. It's not like Robert. And he goes, I prefer to be called Bob. Oh, it's Bob, right? The baby came out like, oh, that looks like a Bob, baby Bob, So anyway, she's no nonsense. Yeah. So let's try and get back to that. I'm sorry, you've been occupying your time with Minesweeper and English.
He's not that good.
No? Well, here's what we're saying. Not canyon, sine of x and tangent of x. As we approach 0, they are not only similar, they are the same. They are exactly the same. If you were to graph tangent of x and sine of x on your TI-83 calculator, and you were to zoom in repeatedly, you would see the same graph. In fact, do you want to do that? This is where we're going kind of like off on a tangent, which is a calculus term. But it's not going to be on the AP exam, but you know what? It's kind of cool. It's kind of cool. It kind of increases your understanding of what's going on. And I think that's kind of the real benefit is the hunger, right? The quest for understanding, not just for getting the right answer. Just tell us how to do it. No, let's explore. RAM cleared. Okay, good. It's like walking into a clean bathroom, It's like, yeah, all right. Not the 900 wing. What are we graphing? We're graphing, let's do alpha y equals. Okay, I'll do x divided by sine of x first. Okay, and then down here in y sub 2, I'm doing the wrong thing. I wanted to graph sine of x and tangent of x. I don't even know what I want to do. I'm fickle like that. My favorite number is x. That's how fickle I am. Tangent of x. Okay. Now, what mode should we be in? Yeah, we should be in radian mode all year long, never out of radian mode. Okay. Now, I want to go ahead and manually set the window. Let's go from negative pi halves. Oops, negative pi halves. You can always hit on to interrupt the graph most of the time. Whoa, stop. Yeah, hammer time, right? Break this thing. Okay, window, negative pi divided by 2. And then we have pi divided by 2. Okay, that's our window. And then y min, y max, I'm just going to go from like negative, let's go from negative 0.5 to 0.5. That's still quite expansive. But here comes the graph of Sahala. And here comes the graph of tangent. Say what? Okay, so we do have tunnel vision here, and that's good. That's good. I'm going to do this now. I'm going to hit zoom. Zoom 6 is a standard window, but I'm going to hit zoom 5. Zoom 5 is a square window. You know what that does? It makes the markings on the x and y axis the same. Okay, so sine was the first one that came in there that's curving upward and then downward, and tangent is the one that comes in on the bottom. So by zooming in on a square window, it's not like horizontally stretched. Okay, now let's do this. Zoom in, zoom number 2. It's blinking at the origin. That's near 0, isn't it? Let's zoom in, right? We're zooming in. So this is about how far Mara was zoomed in before lunch when she said they're similar. And at this point, they are still just similar, right? Because did you see this little blurb of pixels at the bottom and the top? That's where they're different. But everywhere else, between those blurbs at the top and bottom, the calculator can't really tell the difference between the graph of sine and the graph of tangent. I'm going to do this. I should have done this. Let's go back down to tangent, and I'm going to go to the left, and I'm going to hit enter once. Now, if you have a color calculator, you get to see it trace over. But if you don't have a color calculator, one way to kind of see the tracing over is to make it bold, all right? So if we go back to graph, we're in the same window. There's sine, and here comes tangent. Still see the blurb. Now, we're going to zoom in again. Zoom number 2. We're in a square window, so everything is scaled the same on the X and Y axis. We're blinking at the origin. I'm going to hit enter. Here comes sine. Here comes tangent. Do you see the blurb at the top and bottom anymore? I don't. It's still blinking at the origin. That's still near 0. I'm going to hit enter again. We're zooming in, right? This is farther than humanly possible, but yet here we are. Hey, one more time. What do you say? You want to get crazy with the capital C? Crazy. Do it again. Right? All right, there you go. We are close now, baby. Like two couples should be, right? You don't know where one ends and the other begins. That's a good couple, right? Hey, let's go to the table. Table. Where's the table? Do we have a table? Yeah, it's second graph, okay? Now, it's automatically set up by default to generate for integer values of x, 0, 1, 2, 3. Look at the y values. I'm going to scroll up so we can see on either side of 0. At 0, they're the same for sure, right? Let's go to our scale. Let's go to table set. We'll start at -1. And let's count by not ones. Let's count by 0.001. Holy moly. That's counting by a small scale. And now I'm going to go back to the table. Oh, I want to start. Let's start at 0 because it's too small. Let's start at 0. So I'm starting at 0 and I'm counting by 1 what? 1,000th, okay? And then if I hit the table, you go calculator. So if I click up, now I can see on the other side. So this is numerically zooming in on either side of 0. Does there appear to be a difference in those values in the table, in the y column? Well, there's subtle difference close to it, but look at after at 0.002, the two y values are the same. 003, the two y values are the same. So at least to 3 decimals, they are the same. Now my question is, are they really actually the same? No, okay, they're not. But near 0, they are effectively the same, okay? They are exactly the same at 0. That's the only place they share a y value. But in the neighborhood of 0, that is immediately to the left and right. They are so close to each other, they might as well be the same thing. Now here's what else is cool about them. You could think of both of them as launching out of the origin with what slope? This gets into chapter 2. If you zoom in close enough, this is called differentiability, or the idea is called local linearity. If you zoom in on a curve close enough, you don't see the curve anymore. You start seeing a line. So like TVs are made up of individual pixels, and the more pixels you have, the better the resolution. You can think of graphs as being made up not of pixels, not of dots, but of infinitely small little lines that are tangent lines. This would be the tangent line to sine of x and cosine of, or sine of x and tangent of x at 0. What does the slope of that line appear to be? I'm in a square window now, so. It looks like 1, right? It looks like it's launching out at a 45-degree angle, which is a slope of 1, up 1 over 1, up 1 over 1. Well, guess what? It is. It is, okay? That gets into what we call the derivative, the slope of a curve at a point, or how fast is a graph changing at a single moment. If you can zoom in on that graph, you'll start seeing not a curve, but a line. And it's not just any line, it's the tangent line at that point. And if you can find the slope of that line, you know the instantaneous rate of change of that curve. So it turns out that not only do they have the same y value at 0 and in the neighborhood of 0, but they have the same rate of change, the same slope in the neighborhood of 0. That makes them effectively interchangeable. So there you go. I did go off on a tangent for that, but I don't know. I don't usually do that, but I think it's fascinating. So what that means is we can come up here. Remember all this stuff we memorized where here was sine? This line right here. Well, guess what? It still works with sine, but guess what else it works with now? It also works with tangent. So I'm just going to copy that dude. I'm going to paste him up here. And then I'm just going to come in with my eraser and get rid of the sine. And I'm just going to replace it with tangent. Okay? It works with sine. It works with tangent. They're interchangeable at 0. That's fascinating. So that expands again. That expands our repertoire, our memorized repertoire. That's a great word, repertoire. Spelled differently than it sounds. Okay. So what would this be? Let me give you a quick example then. What would be the limit as x goes to 0 of tangent of 12x? We'll make it like that. 12x over 14x. Yeah, you get 0 over 0, right? Never not first. 0 over 0. And so you do get 12/14, which on a free response you can stop, but if you simplify, you get 6/7. Yeah. And that could also be flipped as well, right? The tangent can be in the bottom. All right. So good so far? So far, so good? Fun, 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 fun. Okay. So now we're ready to, well, let's do this, dude. We got to get C out of the way. We got to get C out of the way. Okay, there's that extra example. You go over there. All right, look at this. This one's kind of fascinating because the variable is not x, it's theta. Ooh. So the limit as theta goes to 0 of secant of theta minus 1 over theta secant theta. Never, ever, never, ever, ever not first. Direct substitution. What is secant of 0? It's the reciprocal of which trig function? Cosine. It's the reciprocal of cosine. So cosine of 0 is what? 1. What's the reciprocal of 1? 1. Yeah, okay. So cosine of 0 and secant of 0 are both 1. So in the top I get 1 minus 1, woohoo, which is 0. And in the bottom I get 0 times secant of 0, which is 1. 0 times 1 is 0. So I get 0 over 0. Yes, sirree. Yes, sirree. Does the factor and divide out method work here? Can I divide out this theta from the bottom like this? Oh, yeah. Oh, yeah. Magic trick. No, it's not a magic trick. It's a bad math joke, right? That doesn't work. But you know what? We're approaching 0, and I do get 0 over 0, and I memorized, as you did, 2 limits involving trig functions that were in terms of sine and cosine. Now, here's what you should remember about all the other trig functions besides sine and cosine. You can write all of them in terms of sine and cosine. Every single trig function can be written in terms of sine and cosine. Let's review them real quickly. We had the tangent one over here. Whoop. You can find these on my website as well. Tangent is that. Let's get this one out of the way. Cotangent is the reciprocal, cosine over sine. But we also have secant of x. Y'all said it was 1 over cosine. And then cosecant of x is 1 over sine. So if you're ever approaching 0 and you find yourself in a triggy situation, try to put everything in terms of sine and cosine. That was kind of one of, if y'all did proofs last year, I don't think we got to them in honors. Did we? Okay, good. Okay, man, y'all must have had a good teacher.
I know we did.
The last resort, if you're doing a proof, is to get everything in terms of sine and cosine. Puts everything on a level playing field. Okay, and it doesn't have to be a last resort. It could be your first strategy. So look what happens over here if I do that. I'm working straight down, so the limit of theta goes to 0. I get 1 over cosine of theta minus 1 all over theta times 1 over cosine of theta. Now, if you don't like theta, is it okay to change it to x everywhere as you write it down from one line to the next? Absolutely. Just make sure you start using x everywhere. You can redefine it. You can use Omicron if you want. That's another Greek letter. I don't even know what it looks like. All right, now, At this point, you should be celebrating, right? Hooray, hooray, I say today, for today is my lucky day. Because we just created a what? Complex fraction. And anytime you create a complex fraction, the next algebraic step is always to eradicate it, get rid of it. And in this case, you can't do state change flip, right? You like my little Boston Terrier. State change flip? No. Because you have two terms in the top. I guess you could, but it would be funky. So we're going to use the lick 'em over lick 'em method. We've already used that. My miniature denominators are cosine. That's it. What's the LCM of cosine and cosine? That's a funny question. It's cosine, right? So we're going to multiply by cosine over cosine. And by the way, you could multiply by the reciprocal of 1 over cosine in the bottom because it is a single term. But let's do lick 'em over lick 'em. All right. So again, you're kind of extending this purple bar across that way. And now on the top, you have to distribute. If you distribute cosine times 1 over cosine, that's 1, right? Minus cosine times 1 is cosine. All right. Sweet. And in the bottom, I multiply. There's no distributing. It's just one term. So the cosines divide out. And I'm left with what? Theta. I've changed its complexion, right? The phenotype is different, but the genotype is the same. Or maybe opposite. Yeah, no, that's the same. Let's try. Yeah, go ahead.
How does on the bottom, how does it distribute?
It's not distributing. See, there's only one term in the bottom. This is theta times 1 over cosine. It's just one term. In the top, there's 2, so I have to distribute. So in the bottom, I can just multiply any terms, any factors together in any order. So I just multiply the 1 over cosine times cosine. You don't distribute to here. So it's this times this times this. These divide out. We're left with that. Now, do you recognize this? Holy moly. That's the dude. That's what we memorized. That is what? Is that the one we memorized that goes to 1, or is that the one that goes to 0? Oh, 0. Dang, 0. Oh, you don't want to get all that way and say it's 0. I mean 1, sorry. Now, look. This was the one we memorized in disguise. Now here's an easy way to remember it, or not. I don't know if it helps. I really haven't figured out a way to determine which one goes to 1 and which one goes to 0. I don't know. So if that helps you, if it works, it works. The sine one goes to 1, the cosine one goes to 0. If you want to draw a line through the 0 so it looks like a computer number, that's up to you. Okay? Because otherwise it looks like the letter O. I am a computer 0. I do my own thing. In mathematics, that looks a lot like what we call the null set. So you got to be careful. All right. So I'm going to take that. I don't like it there. All right. So that could help you. All right. Moving right along. Duggadoon, duggadoon. Everyone good? All right. Let's go deeper down the rabbit hole. What the heck, moly? Well, never not first. We're going to 0. What do we get in the top? We get 0. 5 times 0 is 0. Sine of 0 is 0. 0 times 4 is 0. Boom. And in the bottom, we get what? We get 0. 2 times 0 is 0, but cosine of 0 is 1. And 1 times 0, alas, is 0. But it's not alas, it's like, heck yeah, right? So this is one giant term, isn't it? So you can associate the factors in any order you want. Can I associate sine of 5x over x together? In other words, let's do this. This is what you could do mentally. You don't actually have to physically write it out. We can do that, and then times, you can give the other limit to this guy. You want to isolate the bad guys. Who's causing the 0 over 0? Right? I can do that using two properties. The associative property of multiplication allows me to group those factors in any order. And the properties of limits from 1.2 says I can take the limit of the products to get or the product of the limits to get the limit of the product. Now, by memorization, what is the first limit there? It's sine of 5x over 1x, right? So that's 0 over 0. We should get 5 over 1. Yes? Yes, by memorization. And now, how do we evaluate the other limit, the other factors? What? Just plug it in, right? There's no sense in calling that other set of factors bad guys, like we did sine of 5x over x. These guys are causing all the problems. That's the 0 over 0. This other factor group over here, they're not causing trouble. When you plug in a 0 to cosine, you get a 1. These guys are causing a 4. Ooh, that's not bad. So direct substitution, right? And we do get a 4. So we get 5 out of the first by memorization. We get a 4 out of the second by plugging it in. And of course, the answer is 20. Boom, chakalaka, boom, chakalaka, boom. Boom, chakalaka, boom. Okay? So there you go. The associative property of multiplication is fantastic. So in the future, you could just like mentally group those together and say, oh, that's 5 over 1, boom, that's 5, and then I get 4 over 1, that's 4, 5 plus 4 is 20, boom, I'm done. Yes, next, please. All right, see if you can figure this one out. Letter E, chew on it, chew on it. We'll call this dessert after lunch. Kind of give you the insight. Okay, we do get 0 over 0 when we plug in. We memorized a sine rule as we approach 0. We know that we can replace sine with tangent near 0. They're interchangeable, right? So what happens when they're together? Well, let's do this. Let's say it's tangent of 3x over something times something over sine of 4x. That's legal, right? As long as we put ones here and here. That's legal. Now, here's where we are going to create what we need. We're going to call that other factor kind of like the I have to have factor because of math, right? I wish there were a what in the denominator of tangent of 3x. Really anything, right? It could be an x. It could be a 3x. Let's just put an x, okay? Because if that were tangent of 3x over 1x, we memorize that as we approach 0 to be 3 over 1, yes? So I can put an x, not just a variable. I can put an x in the denominator as long as over here I put an x in the numerator, right? That's cleverly multiplying by a clever form of 1. And then similarly, I wish in the numerator of the sine of 4x, I wish there were a what? I wish there were an x, because then I can call that 1 over 4. Well, I can do that so long as I divide by x somewhere else in the problem. Yes, you got it. You got it. All right. So now I have 3 factors. I could take the limit of each one of them separately. By memorization, what's the limit of the first factor? 3 over 1, which is 3. Times, by memorization, what's the limit of the next factor? 1/4. Good. And of course, what is the limit as x goes to 0 of x over x? 1. That extra stuff that we needed divides out anyway. In fact, you wouldn't have to do that. You could have just said, oh, they both need an x. I'm going to multiply and divide by an x like that, if you want to do it that way. And then you don't even have that third factor, which divides out to give you 1. So the answer is 3/4. Now, as the bell approaches, you're like, hey, wait a minute. Is the 3/4 we got in the answer the same 3/4 that we were staring at in the beginning? We'll find out tomorrow. No, you don't have to show work for that.